So as we continue looking at functions, a couple other interesting features they can have is some symmetry or maybe some asymptotes. For symmetry, there's two main types that we're going to look at. Even functions are symmetrical about the y-axis. So let's look at if we had the 0.25, if we're an even function. So maybe picture it here. If you have this 0.25, well, if it's symmetrical about the y-axis, across the y-axis, if this is 2,5, that has to be negative 2,5. 2,5, negative 2,5 across the y-axis. So this point would have to be on the graph as well, which means that in general, it doesn't really matter whether you're plugging in a positive x value or the opposite x value, the negative x value. So f of x and f of negative x are identical, are equal. F of the opposite of x and f of x are the same thing. The other symmetry is what we call odd functions, symmetrical with respect to the origin. And so this was more of a reflectional rotation. If you just kind of flip across the axis with the origin, that's more rotational symmetry. So if you take something, if you picture kind of rotating 180 degrees upside down about the origin, if it's the same thing, that's an odd function. Or just kind of go across the origin if you can get kind of the right angle to it, and it should be there. So let's picture this one. If we had 2,5, if we had this point 2,5, and we're symmetrical across the origin, what we would have if we take this point and then rotate it 180 degrees like that, what point would we end up at? Well, we go from positive to negative. So 2,5 on the graph, we'd also have to have negative 2, negative 5 if we're an odd function. So now if we compare f of negative x and f of x, this isn't true anymore. They're not equal. The positive x value and the negative x value give us different y values, but there is a relationship. One was 5, one was negative 5. So if you plug in the opposite x value, you get the opposite y value. All right, so we're going to want to determine even, odd, or neither. Not every function is even or odd, of course. There's plenty of functions that aren't either one. We'll do it algebraically first, and then we'll take a look at the graph and make sure that makes sense. So algebraically, what we're going to use, if we want to do algebraically, we're going to use this right here. And so we're going to use f of negative x to determine algebraically. So let's replace x with negative x. So, and by the way, really it should be, we should say that the opposite of x, because negative x, if x was negative, negative would be positive. So this, what looks like negative x might actually be a positive number. So really you're supposed to call it opposite of x, but for the sake of time, I'll call it negative x. So then what happens here? Well, if you square a negative, squaring a negative, you just get a positive. So that negative is going to go away. We're just going to get x squared plus 1. Well, that's the same thing as what we started with. That's the same thing as f of x. So this right here is an even function. So plug in negative x, get the same thing. It's going to be even. If we take a look at the graph, this is a pretty simple one here. Parabola shifted up 1. This should make sense. This is symmetrical across the y-axis. It's the same on both sides. If I kind of folded my paper along the y-axis, if I did a fold there, this part of the graph, if you folded it, it would land on that other part of the graph right there. It's got that symmetry. All right, over here, again, we'll start with algebraically. We'll replace x with negative x. See what we get. Well, this one, if you cube a negative, 3 negatives, it's still negative. So this negative is not going to disappear. It's still going to be there. That's going to be negative x cubed. And then minus a negative, that's plus x. Okay. So this one I plugged in a negative, and take a look what I got. I got the exact opposite of what I started with. So you could probably say your answer right there. Technically, what you really should do is factor out a negative and see what happens here. So, well, if I factor out this negative, that's negative g of x. I got the opposite of what I started with. So this one is odd. Okay. And to take a look at the graph to confirm this, you could just use your graphing calculator. This is actually one of the same functions from the previous lesson. So I can just I'm going to draw the graph for us quickly here. It would look like that. And so that does definitely look odd. Not odd as in strange or weird, but an odd function, that symmetry about the origin. So if you take a look at any point, go across the origin, that point is there. Or again, if you rotate it 180 degrees, about the origin. It's got to be about the origin. So if I put my pen down there to kind of hold it, and then if I turned it 180 degrees, it looks pretty much the same as it did when we started. Right, so another one here. Start by substituting in negative x. And again, if it's that odd exponent there, the negative is going to stay. So you might start to kind of get an idea of where the names came from for even or odd. There's other cases as well, but in general, odd exponents tend to go with odd functions, even exponents tend to go with even functions. And so right here, let's take a look at what happened. The first term changed. The first term is the opposite, but then the second term didn't change. This one's kind of a mixture. Staying the same was even, and then getting the opposite was odd, but this is a mixture, so that means this one is going to be neither. It's not even or odd. If you really want to convince yourself, you could factor out that negative, and you could see, well, it's not the same thing as negative h of x. It's also, of course, not the same thing as h of x. It's just neither. If you take a look at this function here, it's going to look something like that, which is very close to odd symmetry, but it's not about the origin. This one you could say was maybe symmetrical about that point right there. Could have rotational symmetry about that point, but not about the origin. If you look at this section here, there's no corresponding section across the origin there. All right, so that's even, odd, or neither. It's determined algebraically. You're plugging in negative x. So why don't you guys go ahead and try these next two problems here. Go ahead and give number 4 and number 5 a try. Plug in negative x to see if it's even, odd, or neither, and then you can use your calculator to take a look at the graph and make sure it matches what you found. So go ahead and double check your answers right there. You should have found that the first one was neither. The first part changed, the second part didn't. If it's a mixture, that's going to be neither. And then you can see that from the graph. This section here, there's no corresponding section across the origin. If you turn that around, it's not going to look the same. And then this one was even. Doesn't matter if we take the absolute value of a negative or a positive. Just make sure you know in your work, which I'll be looking at for tests, right? In your work, you got to have the absolute value of x there. I've noticed students sometimes just replace this with x. Absolute value of negative x is not the same thing as x. It's the same thing as absolute value of x. You got to make sure you're keeping this positive here. If x was a negative number, then it wouldn't make sense to just have x right there. And also, you want it to match the original function. You want it to be exactly the same as what you started with. And if you graph that, it almost just looks like a parabola. It's a little bit more pointy down close to the center there. It's a little bit steeper because it's x to the 4th instead of x squared, but it's still got that symmetry across the y-axis. Well, so now let's go ahead and take a look at asymptotes. So asymptotes are lines that the graphs approach, get really, really close to, but don't quite reach. So you might have noticed the image for our course in Canvas says, I'm an asymptote, can't touch this, like the MC Hammer song there. So this graph just gets closer and closer and closer to this line. They get as close as you want. Super, super close, but they never quite reach. Can't touch this. Super, super, super close, but doesn't quite hit it. Right? So we can either have a vertical line or a horizontal line. That's an asymptote. And so if it's a vertical line, what's happening is that as the graph gets closer to this x value, so as the x values get closer and closer to this number for this vertical line, the y values are either going to go to infinity, or you could have one on the bottom here. You could also have the y's going to negative infinity. And so what happens is, since there's this vertical line that we don't touch, whatever x value is for that vertical line, we don't have a point for that x value. So if we don't have a point, it's because the function was undefined. And of course, the thing that we've seen where a function can be undefined is when the denominator is 0. So if we look at a function like this here, the vertical asymptote is always going to be x equals. And so our vertical asymptote here would be x equals 2. X equals 2 would be the number that would make the denominator be 0. But horizontal asymptotes are a little slightly more complicated. Again, it's the same idea. We've got this line the graph gets really, really close to, doesn't quite reach. So it's a y value that there's no point on the graph for that y value. What's going to happen with this one is it's always going to be as the x's either approach infinity, or it could be on the left side. You could have a graph approaching it on the left side. So it could also be the x's getting close to negative infinity. So it's as x goes like 100, 1,000, 10,000, a million, a billion, as x gets really, really large, that's when the y values get really, really close to whatever y value is the asymptote here. Like if x is 1 or 2 down here, it's not close. So it's when x gets really, really large that you start to approach this asymptote. And so because of that, I'll explain in just a second. What happens is, define the asymptote, you actually look at if the degrees of the numerator and denominator are the same. So again, the degree is the highest exponent. Hopefully you remember that from your previous classes. If those degrees are the same, then you can look at the ratio, the fraction formed from the leading coefficient. So you look at the numbers, the coefficients in front of this term with the highest exponent, with the degree. So if you look at those two, that's going to be your horizontal asymptote. So why the heck does that rule work? What is this random rule talking about? Okay, it comes from, again, we're looking at what happens when x gets really, really large. So think about x approaching infinity. All right? If x is a billion, a trillion, a quadrillion, a Google, a number that's a 1 with 100 zeros after. If x is so large, this plus 1 doesn't really matter that much. If x is a billion, this function is not going to look much different at all if I just deleted that plus 1 right there. What about a minus 5? If x is a trillion, minus 5 doesn't really matter that much. Kind of like to explain it like if you're Bill Gates and you're walking down the sidewalk, are you going to stop and pick up a penny? Probably not. You've got so much money, you're probably not gonna, you're the time that you would spend bending down to pick up the penny, you probably could have made $100. You're risking maybe your back goes out or something like that. If you've got that much money, you're not gonna care about a penny on the sidewalk. I think, I don't know. Maybe Bill Gates likes to collect pennies. I don't know, but probably not. If you've got that much money, you don't care about a penny on a sidewalk. Okay. In fact, what happens here is when x gets so large, a trillion, a quadrillion, unimaginably large numbers, 4 times x is so much smaller than x cubed that actually 4 times x starts to not matter either. And in fact, a billion cubed is so much larger than a billion squared that even this term starts to not matter. It's only the highest order terms, the highest exponent, the ones that grow the fastest, that are really going to matter when x gets really, really large. And so if all those other terms are basically insignificant at this point, then the x cubes could cancel out as well. And so we would just be looking at this 3/2, this ratio of the leading coefficients. And so the horizontal asymptote, this y value, this horizontal line that the graph is going to approach for large x values, would be 3/2. Okay. Now, if you look in most textbooks, they're going to have three different rules for horizontal asymptotes. They're going to have a rule for when the degrees are equal, and then they're going to have a rule for when the degrees of the numerator is greater than the denominator, and a rule for when it's less than. If you like memorizing different rules, you can look in your textbook. You can memorize those different rules. But actually, when I was a student at Helix High School, sitting in my honors algebra 2 course, I thought that it was kind of silly to have three different rules to memorize, and I actually came up with a trick where you can just use the one rule. So the trick that I thought of is, what if we made them kind of look like they had equal degrees? So what if I added in a 0x squared in that numerator? Now, technically, I haven't changed the degrees. Technically, the degree of this is still 1. But it's just a trick. It works. I can now pretend like the degrees are equal, and I can look at this ratio of the leading coefficients. Of course, x squared is the same thing as 1x squared. And so if I've got 0 over 1, well, 0 over 1 equals 0. So my horizontal asymptote is 0. What about this one here? This one, I would need a 0x cubed in here. I'm using 0, of course, because adding 0 doesn't change anything, right? 5 plus 0 is still 5. So if I put a 0x cubed in there, well, if I take a look at this ratio of the leading coefficients, now I've got 1 over 0. Well, if you've got 0 in the denominator of a fraction, that's undefined. Now, here's the only thing with my trick. If you put undefined, you're not going to get full credit. You can't say undefined. What do you think that means for a horizontal asymptote? If it's you can't have y equals undefined. You can't equal undefined. If it's undefined, that means there's none. There's no horizontal asymptotes. Okay. All right, so let's take a look at some examples here where we try to find both. So for the vertical asymptote, you're looking at the denominator, when the denominator would be 0. So x plus 1 equals 0. That's x equals negative 1. Then for the horizontal asymptote, we've got equal degrees here. They're both x to the first. And so I can look at this 2 over 1 here and say y equals 2. Notice I do want them to be equations. It's really important that you know the vertical lines are x equals and horizontal lines are y equals. I am going to be a stickler about that. Asymptotes, you've got to write them as equations. Okay. Now for number 2 here, so for A, we want x squared plus 1 to equal 0. Well, that would mean that x squared would equal negative 1. That would be x equaling plus or minus the square root of negative 1. Well, we can't square root negatives. Now, you probably did a little bit of imaginary numbers in Algebra 2, so you know that they are a thing. But anytime we're talking about graphs, imaginary numbers are not a thing. Graphs are only real numbers. When you're using the Cartesian plane, x, y coordinates, x-axis, y-axis, graphing on there, those are only real numbers. And asymptotes are things that show up on a graph. So we're only doing real numbers. We can't have imaginary numbers. So we're going to say none. There's no vertical asymptotes. Can't give me imaginary numbers. Right? For horizontal asymptote, now they're not equal degrees here. So you've got to use my trick, add in a 0x squared. And so we would have 0 over 1. 0 on the top is 0. So y equals 0 is our horizontal asymptote. All right, for this one, now we want x squared minus 1 to equal 0. That'll give us x equals plus or minus 1. We can have multiple of the same type of asymptote. You could have 10 vertical asymptotes, theoretically. Now, technically, we should write them separately. These aren't just x values, solutions to an equation. These are lines. Technically, we should write the two different lines separately. And then on this one, we'd have to put 0x cubed plus in the denominator. If we have 0 on the bottom, that's an undefined fraction. Do you remember what to put for horizontal asymptote? If this fraction is undefined, that means there are no horizontal asymptotes. None. I want you guys to go ahead and give those last couple problems a try there. Find the vertical and horizontal asymptotes. Make sure you give me the equations. And you can check your answers here. Um, Notice that for number 4 here, you have to look at what would happen if you multiply out 2 minus x squared. I mean, you can write it out if you want, x squared minus 4x plus 4, but all you need is this first term here, this denominator, the leading term, the degree, and the leading coefficient. Degree is 2, leading coefficient is 1. For number 5, just make sure you solve that denominator one carefully. Sometimes people go a little too fast and miss that there's those roots there.